All right, ladies and gentlemen, I think I got everybody in. So today what we're going to be doing is we are actually going to be looking at something we did a while ago. We're going to look at our mechanical energy POGL that you guys did a few weeks back. So on Canvas, on your weekly agenda, you should be able to see it if you did not ever open it, or in your Notability or Zoom, wherever you have it. Or Canvas, wherever you save all your documents, please try and find it and open up to Springs on page 4, because we're going to be going back. Recently, we've just been doing our gravitational potential energy and we've been doing kinetic energy, but now we're going to go back and we're going to talk about springs just a little bit. We're going to get back into that part of our unit so we can add all of our types of energy all together. So it says in this section, I'm just going to read it pretty quickly. Hopefully, if you have any questions, just stop me. But it says that without looking at the chemistry of batteries, which is another course that's super cool, but we're not interested in it for today, or the energy released by burning large macromolecules like sugars and oil, which is also pretty fascinating chemistry, still not this course. There is other ways of storing energy. So one of them is springs, or an object that wants to return to its original shape. So any elastic object like rubber bands or an archer's bow or sweatpants with their elastic waistband, a spring could apply a force and cause something to move, which means that it has the potential to do work and therefore it can store energy. So just like our gravitational potential energy is at a specific height and it has that energy stored, this time we are compressing or expanding springs with that potential to return to its original shape. So it depends on two things. So the distance the spring or the elastic object is deformed from its equilibrium state, which is just a fancy way of saying how far it's been stretched or compressed, and the relative strength of the spring. The different sizes will obviously exert different forces. Think about the spring in your pen or pencil at the top versus the one holding a truck suspension. Obviously, the amount of force required to compress each is different. So we're going to consider a situation of pushing frictionless object horizontally across the floor into a spring braced against the wall. So like the figure to the right. An applied force to the left is being counteracted by the spring force pushing back to the right. Let's set them equal to each other so that the box is moving at a constant velocity, which means there's no acceleration. Work is done on the box because the force is being applied to it over some distance. The energy isn't being stored as gravitational potential energy because there's no height change on this box, nor is there kinetic energy because the speed of the box isn't increasing. Where does this energy go? The answer must be spring. The energy getting stored in the spring, meaning the spring has the potential to do work. So we're not sure what happens if the applied force of the box is removed. The spring will apply its force and push the box some distance to the right. That is doing work. The deformation of the spring, so being stretched or compressed, is measured by the change in length, and it's the variable x. A 1.2 meter spring compressed to 0.8 meters will have a compression of 0.4 meters. That's also the same as if we have a 1.2 meter spring and it's being stretched at 1.6 meters. Interestingly enough, the energy stored in the spring is the same for both scenarios because they're both being either stretched or compressed 0.4 meters. They'll have the same amount of energy done or stored. The strength of the spring is referred to as the spring constant, which is K. The spring constant is a ratio of the force applied by a spring, the spring force. to the distance the spring is stretched or compressed to apply that force. So an example, a spring force of 50 newtons stretched 15 centimeters. The spring constant K for this spring would be 50 newtons divided by the 0.15 meters, because we always want it in Newton meters, and is equal to 300 Newton meters. Down below here, these definitions down here, I am going to leave that up to you since you should already have those. I do want to talk about one of these exercises from exercise 4. So just to get our work down to see if we can calculate these spring constants and therefore calculate the energy and the force by these springs. So this scenario says the suspension of the truck supports its weight, which is 8,000 kilograms, and compresses 6.4 centimeters. So the first thing we need to do is figure out what this is going to look like. So we have our truck, which I'm just going to draw as a line, and we have our suspension for that truck, which is going to be a spring, which is going to look like that, holding on by its wheel. The object that we're looking for, the object in question, is going to be right here. So if we draw our free body diagram for this, what kind of forces do we have on this object? Who can tell me a force?
Spring force.
Awesome, the spring force. And which way does that spring force go?
Up.
Up, perfect, because the spring is above the object, so it's going to go up. F sub S. All right, what other force or forces do we have on this object?
Gravity.
Gravity, which way does gravity go?
Down.
Down, all right. Should my gravity force be the same length, bigger or smaller than my spring force?
Would it be the same?
It would be the same because we're not going through the ground, so it's not going to be longer. We're not flying up into the air every time we're driving, which means the spring force isn't going to be larger than gravity, which means they should be about the same, which means if we're solving for our forces, we know that our spring force is going to equal the force of gravity. If they're the same length, that means they're going to be the same value, which means they're equal to one another. All right. So real quick, who can remind me just the general equation to find force?
F equal ma.
F equals ma. Perfect. All right, and we have that force for the spring, which is the spring constant multiplied by the compression or stretch of that spring. And so let's look. Do we have the spring constant? Is that something we were given? Taking that silence as a no, which would be correct. We're not given the spring constant. So that's not one of the things we can solve for here. But we do know that our spring force is equal to our force of gravity. How do I find my force of gravity? Just
Mass times gravity.
Mass times our acceleration due to gravity. So mg, just a little bit different than this one up here because our acceleration is a specific number. And so if we plug in those numbers, we do know our mass over here was 8,000 kilograms. Who could tell me that acceleration due to gravity?
9.81.
9.81. Perfect. That number does not change on Earth. So we have our 9.81 meters per second squared times our 8,000 kilograms. What is that force of gravity or the weight?
$80,000 newtons.
80,000 newtons. Awesome. And we have the 1 sig fig because 1 sig fig from here. All right. So then how am I going to find my spring force?
You already did.
We already did. What value did I get?
80,000 newtons.
80,000 newtons. It's the same as my force of gravity. Perfect. All right. So we found all the forces needed for this problem, but it also wants us to find this K value. And what equation do you think we're going to use to find this K value, this spring constant?
Is it the KX equation?
It's going to be our spring force equation. Perfect. The force of the spring equals K times X, which means just the spring force equals the strength of the spring, or that spring constant, times the length of depression, or how much it's been compressed or stretched. So we have F sub S equals KX. Do we have F sub X? Or sorry, do we have force of the spring?
Yes.
All right, let's plug that in. So we have 8,000 newtons equals K, because that's what we're looking for, times our distance or length of compression or stretch. Do we have that value?
Yes. 6.4 centimeter.
Awesome. So I'm going to put 6.4 centimeters right here. Everybody okay with that so far?
Do you have to change the 6.4 to meters?
We do. We always want our answers in Newton meters or in meters for any distance. So what is 6.4 centimeters in meters?
0.064 meters.
Awesome. All right. So now how do I get that spring constant by itself?
Dividing both sides by the 0.64.
All right. What is my spring constant equal to then?
One million Newton meters.
1 million newtons per meter. Does anybody have any questions on how we just solved that? All right. Just because we should have already completed this puzzle at some point, I just wanted to go over solving one of those just to get our heads back into the thinking of springs. Because tomorrow we're going to do our homework. It's going to be on springs and using that spring potential energy in our problems, along with our kinetic and our gravitational potential energy. So if you guys have any questions on the rest of those practice problems, either on exercise 4 or on exercise 5, please let me know. But I do want to do exercise 6 with just identifying these different types of energy. So if we go through this, the first scenario says a train is moving steadily up a hill. Somebody tell me a form of energy they think exists when this train is moving up a hill steadily.
Kinetic energy.
Kinetic energy. Why kinetic energy?
Because the train is in motion.
The train's in motion. We got kinetic energy then. Perfect. Are there any other forms of energy here?
Gravitational potential.
Gravitational potential. Why gravitational potential?
Because it's going up the hill.
It's going uphill, which gaining height, which means it has the potential to come back down. Perfect. It's changing its height, which means we're gaining potential, gravitational potential energy. Is there spring potential energy for that one? I'm going to take that silence as a no, and that would be correct. What about the next one? A basketball flies through the air in a parabola. What kind of energy do we have there?
Kinetic and gravitational potential.
Why kinetic and why gravitational potential?
The ball is in motion and it's in the air.
Perfect. What about the next one? A bird sitting on a tree branch.
Just gravitational potential.
Just gravitational potential because we have height from the tree. What about a pair of leggings are stretched around some legs?
Spring energy.
We have spring potential energy. Why spring potential energy?
Because the leggings are being stretched.
Exactly. We have that elastic object being stretched, which gives us this spring potential energy. What about a paper clip holds paper together?
Also potential spring.
Also spring potential, perfect, because our paper clip wants to return to its original shape and it's being stretched to hold those papers together. What about a football player running down the field?
Kinetic.
Kinetic energy, they're moving. What about a rubber band is stretched and then fired in an arc?
All three.
All three, perfect. We have gravitational potential from being fired in an arc. We have kinetic because it's moving, and we have spring potential because it's being stretched. What about a ship sinks to the ocean floor?
Gravitational potential and kinetic.
Awesome, because we have that motion of the ship sinking, and we have the height because it's changing its height. What about Pascal launcher fires a ball straight up into the air?
Kinetic and gravitational potential.
Kinetic and gravitational potential, perfect. We got the height when it gets shot in the air, and it's moving as it goes up and comes back down. What about a rock sits and does nothing?
Would it be none of them?
It would be none because it doesn't tell us it's at a height, which means it doesn't have to have gravitational potential energy. It doesn't have any elasticity, so it's not spring potential energy, and it's not moving, so it doesn't have kinetic energy. So none of those energies exist right now. What about a bullet is fired horizontally from a gun?
Kinetic and gravitational potential.
Kinetic and gravitational potential. Perfect. How do we feel about these scenarios? Not too bad. Right, got some thumbs up. Awesome. All right, so then guys, today I really don't have anything else for you to do, which means that things that you need to do are just make sure that you finish up any of those missing parts to this puzzle. If you have any left, or if you have questions you're asking. Otherwise, just prepare for your homework tomorrow, which is going to be homework 5, which is going to be on springs.